Hello again. This is video lecture 28.3, and we're going to talk about section 6 in chapter 28, in which we're going to discuss the magnetic force on a wire carrying current that's immersed in a magnetic field. There are actually no new ideas here, just a new application of the ideas we've already been talking about in chapter 28. Let me explain. Suppose we have a wire carrying electrical current, and of course we know current means moving charges. And we've got a lot of pictures here, but if we look at, say, the case 1 on the left, right, we're talking about a wire, and the conventional current I is traveling upward in the plane of the screen. And conventional current means motion of positive charges. Okay, and so it's just a wire. Maybe it's copper, for example. Copper wire. And we've set up conventional current I flowing in the direction shown by hooking up a battery or a power supply. All right, now, either all along this wire or maybe just in some region of it, there might be a magnetic field because maybe this wire is near the poles of a magnet. And that's what this picture is showing. The wire has part of it anyways, is traveling through a region where there's a uniform magnetic field, at least in that region. And that's represented by those green dots that are pretty much equally spaced and coming towards us. So that would represent a magnetic field in there, B, that is coming out of the screen towards us. All right, so that means that if that wire is sitting in that region of where the magnetic field is, and that wire has current in it, and current is moving charged particles, then we already know from the very first section of chapter 28 that a moving charge in a magnetic field can experience a magnetic force. FB equals Q times V cross B. That is the most important idea in chapter 28. Well, then that means that the current carrying wire in the magnetic field can also experience a magnetic force because current is moving charge. Okay? Now, the pictures here on the left and right, well, on the left and in the middle, show in case 1 and case 2, show the same wire with the same region of magnetic field, but in case 1, the current has been set up to go upward, and the diagram is supposed to represent how there must have been a force on this wire to our right to deflect it to the right. But if we take the same wire and just reverse the direction of the current, I, in the wire to go downward, same magnetic field there, the wire we will observe deflects to our left. So there must be a force, magnetic force, on the current carrying wire to our left. So the first thing we realize is that the direction of this magnetic force on this current carrying wire depends upon which way the current is going. And that shouldn't seem too surprising because current is moving charge, and the magnetic force on a moving charge depends upon which way the charge is moving. So let's take case 1 and do a zoom-in view of a part of the wire that's, roughly right about like in there. Okay? And that's what this picture here is on the right. Case 1, zoom-in view. That's a region of this wire that is immersed in the magnetic field B that's nice and uniform and coming out of the screen towards us. That's what the green dots represent. There is a conventional current I flowing upward in the plane of the screen through the wire that just drew the I over to the side. And that's conventional current, positive charge. So that means if our conductor is, say, copper, then what the charged particles, the charge carriers there, are electrons. And so they must have a drift velocity, Vd, opposite to I. So you can see they've labeled that. The drift velocity of one of the conduction electrons is downward. And let's figure out the direction of the magnetic force on that single conduction electron, okay? This is one conduction electron. moving downward in the wire? Well, we just use F equals Q times V cross B, but the Q then would be negative E, so this negative little e, so negative little e times V drift cross B. Let's do the right-hand rule first to get the direction of V drift cross B. You should be able to practice with that. In fact, you should do it on your own. If you need to pause the video, that's fine. Get the direction using the right-hand rule of V drift cross B. Okay, did you get the direction for that, just that cross product, from the right-hand rule with the V drift down and the B coming out towards you to be to our left? Okay, that's the direction of V drift cross B, to the left. That way. But because the particle, the conduction electron, has negative charge, the magnetic force is opposite to that. So the magnetic force, FB, on this conduction electron is to the right. So let me get rid of that. But the force to the right then would be consistent with this picture here on the left showing case 1, showing the wire being deflected rightward. Okay? So really ultimately the source of that deflection of the wire comes from this formula, Q times V cross B. That's one of the things we wanted you to see. But now what we want to be able to do though is calculate the total force on that wire with its current. Okay? All right, so let's just focus now on that single conduction electron. We know the direction of the magnetic force is to the right. Let's get the formula for the magnitude of that magnetic force. FB magnitude. Well, that'll be the magnitude of its charge, little e, and then I've got that cross product. So it'll be magnitude of the drift velocity, magnitude of the magnetic field, sine of the angle between V drift and B, which we should be able to see is 90 degrees. And the sine of 90 degrees is positive 1. So the expression for FB magnitude, which probably most of the books would just write like that for the magnitude, is E V drift B, all meaning magnitudes. Direction to the right. Okay, now that's just one conduction electron. Well, presumably there's a whole bunch of conduction electrons in that wire. So how do we get the total force on the wire? What we do is we just pick a particular length of wire. Here it's labeled L. And we're going to find the total magnetic force on that length, L. Okay, so we're going to find the total magnetic force on all the conduction electrons in the length L of the wire. And call it FB net. Well, I get that magnitude you see right there, little e V drift B for one electron. So we just multiply by a symbol I'll call capital N, which is the total number of conduction electrons in the wire in that length L. And then I multiply that by EVDB. Does that make sense? This big N is the total number of conduction electrons, I'm going to abbreviate that like that, in the length L. But conducting materials have a nice property that every conducting material has a certain value for the carrier density, the number of charge carriers per unit volume, denoted little m. Okay, so really to get the big M, just the total number of conduction electrons in that length L, I'll take the carrier density for this conducting material, little m, times the volume of the wire in length L. Okay? All right, so that'll be little n, the carrier density, and then the volume of wire of length L is I'll call the cross-sectional area of the wire A, and then the length is L. Okay? So little n is the carrier density. All right, now, let's just go down here a little bit more. Now I'm just going to do some grouping. Okay, I'm going to take the cross-sectional area of the wire times the length L, and then I'm going to gather together the carrier density, the charge magnitude of the carriers times the drift speed, and then B. So those things are all multiplied together. I'm just grouping them in a certain way, because the quantity in the middle set of parentheses is the magnitude of the current density, J, in the wire. Current density magnitude. All right, chapter 26. But current density J, I'm going to have to now start erasing up here, okay? Current density J, by definition, so I'm just continuing up here, is current per unit cross-sectional area. Okay? We already did that. We already talked about that. So this is cross-sectional area times length, and then current density is total current I over cross-sectional area times B. And then the cross-sectional area cancels out, and I get the magnitude of the net magnetic force on the length L of the wire. Actually just depends on three things. L, how much current I, and how strong is the magnetic field, B. And that's a handy result, but we do have to be aware of how it was derived, because that will put a slight limitation on it. This is actually the result for a special case, where the conditions were: I had a uniform magnetic field over the length B, excuse me, the length L, over the length L. I have a straight wire that is perpendicular to the direction of B. And then you get that pretty simple result: L times I times B. Now I'm going to go from there to something a little bit more general. But I'll call it for now case 1. Okay? Wire is straight, and the magnetic field B is uniform, at least over the length L. So we want the magnetic force FB on the length L of the wire. Let's look at this picture. There's the straight wire, right? You see it? I can spell the word. And it has conventional current I flowing in the direction shown. Okay? All right. We're going to take the length that we're interested in, which is from there to there. That's the length L. We're going to actually make a vector out of that, which for a straight wire just has length L and points in the direction of the current. And we'll call that L arrow, L vector. And then here's the magnetic field that the wire is immersed in, going off at this angle. Notice that the magnetic field B is not necessarily perpendicular to the L vector of the wire, and there is some angle phi there between the B and the L. Then, the way to generalize the result I had up above, which just looked like that, is that the general result is actually right here. The magnetic force on the length L of the wire is I times L arrow cross B. arrow. Yep, it's a vector product again. This time it's a vector called L, the length vector that's in the direction of the current. So you do L cross B, multiply by I. The I is always positive in this case, and you'll have the direction of magnitude and direction of F magnetic. Since it is a cross product, we know how to calculate the magnitude. FB magnitude will be I times L magnitude times B magnitude times the sine of that angle phi between L and B. Right there. Notice you'll get the maximum magnetic force when the angle phi is 90. When the magnetic field is perpendicular to the L. And you'll get zero magnetic force when the magnetic field B is in the same direction as the L. And the direction comes from the right-hand rule for L cross B. You try that for the L and the B in this picture. Right-hand rule, L cross B, the resultant has to be perpendicular to both L and B, and it will in this case be straight up in the picture. All right, so this result right over here is quite handy and will be used quite a bit throughout the rest of this chapter and enables us to calculate the magnetic force on a chosen length L of a current-carrying wire if the wire is straight and the magnetic field along it is uniform. Now let me just demonstrate to you, I'm going to use a Wiley Plus video, that this really does happen, that this is a real phenomenon. It's not hard to show, okay? And Wiley Plus has a video of it. Okay? Force on a wire in a magnetic field. So let me just run this. All right, you can see you got a wire and you got a permanent magnet. All right, let me just pause it. A wire sits between the poles of a magnetic field. It shows one representative magnetic field vector, B, for the permanent magnet. And we're going to turn on current in that wire with that old-fashioned power supply. Okay? And the current is basically going away from us into the screen. So the L vector for that little region of the wire that's kind of sitting between the poles is into the screen. Okay? I'm going to do the right-hand rule and do L cross B. I get an upward force. And look, it kicks the wire so hard that it can actually jump up out of the magnet. Okay? It's called the jumping wire demonstration. Okay, so it really does do that. All right. Now let's go on. There is another case we need to be aware of that's a bit more complicated. Of course, there's always a complication, isn't there? So we'll call it case 2. And it's really a grab bag, a catch-all for anything that isn't case 1. So case 2 would be the case where the wire is curved, right? It's not straight. And or the magnetic field is non-uniform. Let me do a little picture for you looking at that case to try to make it clear what we mean. Let's go ahead and keep the wire going straight, like so. And we'll say the conventional current I is flowing like so. And this wire is immersed in a magnetic field. And we're going to be interested in the length between there and there. But at different points along here, and this wire is immersed in a magnetic field, but the magnetic field isn't the same everywhere. Right here, it might be like that, and then a little bit farther down the wire, it's in that direction, and then maybe it's a different magnitude, and then that has a little bit different direction, and then maybe over here it's this way. That's a non-uniform magnetic field, B. Okay? You can't go back up here and just use that formula, I times L cross B, because the B is different at different locations. So you have to do the standard calculus thinking. You have to imagine breaking up the wire into infinitesimal pieces, each with its own little length vector, dl arrow. And the direction of the dl arrow is the same direction as the current flow. Okay, so let me now take that wire and let me draw kind of a zoomed in view of it. So I'm zooming in. And here's a little piece of it with a length vector dl, because the current's going that way, right? And we're just going to look at that one little infinitesimal length of the wire, dl. And maybe right there, the magnetic field is that way with a certain magnitude and direction. Then, because that piece is so short, you can assume the magnetic field is uniformed along that little short piece. And then you'll get a tiny little force, dF magnetic, and it'll be I times dl cross B, just for that one little piece. And then what you got to do is that same thing for every little piece, and get the force on each little piece, and add them all up, but they're all vectors, right? So you've got to sum, which means integrate the force contributions from each of the pieces to get the net force. There it is. You have to do an integral. You can bring the I out front because I'm assuming the I is the same at every location in the wire. So I have to do the integral of dl cross B. So you do have to do that integral if the wire is straight, but the magnetic field is not uniform along it, or the wire is curved. So let me show you something else from Wiley Plus. In this case, it's one of the simulations. So let me get to the screen I need. Okay, so now you're seeing, in this animation, a half circle of wire. Okay, the wire is going in a half circle in the XY plane, with the current starting out on the lower left side, and the current's going around clockwise. And we have a uniform magnetic field represented by all those dots pointing towards us, spaced evenly. That's a uniform magnetic field of 1 Tesla coming out at us. And the current going around clockwise in the half circular arc is 1 ampere. And we'd like to find the net magnetic force on this half circle of wire. Well, because it's not a straight wire, I technically have to break it up into little infinitesimal lengths, dl, and then do I dl cross B to get the force dFB on each piece. And that's what the very first piece in the lower left corner does. See the little dl? It's tangent to the wire in the direction of the current. The magnetic field is coming out at us. When we do dl cross B with the fingers of our right hand, our thumb points to our right, so that little blue arrow is the magnetic force on that little piece. And in fact, the animation shows up above. It did the calculation, assuming a certain size for that angle there, and it got a certain expression for the magnetic force. Okay, it's got a positive x component and a very small negative y component. But then we have to proceed to the next little segment. Boom. Now that little segment dl is bent over a little bit compared to the first one because the wire curves. But I still do I dl cross B, and I get the force on that piece, and that's that second blue arrow labeled dF. And then what the animation did is it's added the x components of these two forces and then the y components, and it's showing the total there at the top. And then we'll go to the next segment. Each segment is a 6-degree arc, just chosen for something small, but not too small to become burdensome. There's the next piece with the little dFB on it. And then the sum of the x components of the 3 dFBs and then the y component sum. And then the next arc. Oops. And the total x and y force so far. And then the next arc. All right? And we have to do that all the way along, and we're adding up the x and y components as we go. That's equivalent to integrating, basically. Now we're halfway around, yes? And we just keep going until we get all the way to the other side. And then we discover, when we add up all those little blue arrows, those little forces on those arcs, that the x components all cancel. And I get a nice big negative y component, negative 10 newtons, it turns out. And there's the actual net force right there. Okay? So that's trying to represent to you how you would have to do the integral, right? Integral just means sum up a bunch of infinitesimals. So let me go back to my notes screen. And so what we're saying is, for that semicircular arc, the current I flowing around clockwise, that I have to break it up into little pieces, dl, find the magnetic force dFb on each piece, and then to get the total magnetic force, FB arrow, I have to add up, i.e. integrate, all the dFb's. And that means do the integral of I times dl cross b. You can bring the I out front because every little piece has the same I. And so then you're integrating, dl cross b. Now in this particular case, the magnetic field vector we're talking about, I'll draw 1 dot b, is the same everywhere. It's uniform. It's coming straight out of the screen. So the b part is uniform in this particular application. So when that's true, I'll just show you what you can do in this case. You can take and put the integral with just the dl vector part, and then cross that into b, like that. And that means just take all the little dl's that make up the half circle, like that, and add them up. Now they're vectors. You've got to add them up as a vector. And so what you'll get is I times what I'll call L net vector cross B, where L net vector is what you will get when you add up all these little dl's along the circumference. And when you add them all up, you'll just get an effective L going straight across the diameter. That's the L net. Okay? And of course, the L net, if I think of this half circle, there's the center, having a radius big R, then the length of that L net, of course, is just 2R. And so now I just have a regular cross product. So its magnitude will be I times the magnitude of L net times the magnitude of B times the sine of the angle between L net and B. That's 90 degrees. And the sine of 90 is +1. And the magnitude of L net is 2 times the radius in this particular application. So the result I get for the magnitude of F net is 2IRB, and the direction follows from the right-hand rule applied to L net cross B. Take the fingers of your right hand and push L net on top of B. L net is to our right, and B is coming out towards us, and your thumb points straight down in the plane of the screen. And so that's how you get the net force on the wire downward. And the picture showed that as being the negative y direction, so that'd be negative j hat. Okay? All right, so we will do some practicing in class on calculating the magnetic force on a current carrying wire in a magnetic field. We'll just have to first figure out, we're dealing with the simpler case, case 1, wire is straight and the magnetic field is uniform, or the more complicated case 2, where the wire might be curved and or the magnetic field not be uniform. And then we will proceed from there. I would just leave you with a little bit of class engagement for Blackboard. And it goes like this. We have a figure, as you can see, as well as an XYZ coordinate system. And the figure shows a current I in a wire in a uniform magnetic field, and you can see that the wire is straight. Okay, so I've got a straight wire carrying current I in a uniform magnetic field B. And it shows the direction of I, and there's a magnetic force, FB, on the wire, and it shows which way it points. Notice FB points in the plus Z direction in this picture. Okay, that's the setup. Notice it's a straight wire in a uniform magnetic field. Here's question A. Of course, the magnetic field B arrow, is oriented, is directed, so that the magnetic force is a maximum. Given the picture, what's the direction of B? That's part A. Then part B. All right, compared to the situation in A, where I had a maximum force, and you can see the direction of it, suppose we reverse the direction of the current, I, but not the direction of the magnetic field, B. What now is the direction of the magnetic force? Okay? C. Again, compared to the situation in A, suppose we reverse the direction of the magnetic field, B, but not the direction of the current, I. What now is the direction of the magnetic force on the wire? And then lastly, D, again compared to the situation in part A. Suppose we reverse both the direction of the current, I, and the direction of the magnetic field, B. What now is the direction of the magnetic force on the wire? That's our practice. And then we'll be talking about this also in Monday's class. And that's all for this video.